None of the rectifier circuits we have examined will produce a stable, clean DC voltage. Instead, they produce a pulsating DC voltage called ripple. Since most electronic equipment requires a highly stable DC power supply voltage with minimal ripple, a filter circuit is used at the output of the rectifier circuit. The function of the filter circuit is to minimize the ripple in the DC voltage to produce a pure DC signal which is ripple-free. Basically, all power supply filters are low-pass filter circuits that are designed to pass a DC voltage and attenuate any fundamental and harmonic frequencies greater than 0 Hz. The output voltage from the rectifier circuit will depend upon the type of rectifier circuit used and whether or not a capacitor is used across the rectifier circuit. There are two basic types of filter circuits used with power supplies. First, the choke input type, and second, the capacitor input type. The simplest type filter circuit is a single capacitor placed across the output of the rectifier circuit. The effect of the capacitor is to increase the output voltage and to filter any AC component from the output. Basically, the capacitor stores energy while the applied voltage is increasing and releases it to the load when the applied voltage falls. Usually more filtering action is required, so additional filtering components are inserted between the capacitor and the load. Here we see an RC filter circuit. As you've noticed, capacitor C1 is connected directly across the rectifier circuit output and is followed by a series resistor, then by another capacitor, C2. This circuit will reduce the ripple much better than the simple single capacitor filter. The major disadvantage from this circuit is that it reduces the DC output voltage because of the voltage drop across the series resistor. Also, the greater the current drawn by the load, the lower the available DC output voltage will be due to the increased voltage drop across the series resistor. Let's examine this circuit to see how it works. The positive pulse coming from the rectifier output will charge capacitor C1 to the peak voltage value of the applied signal. As the positive pulse drops in amplitude, the capacitor will start to discharge through the series resistor and into the load. Capacitor C2 will also charge as the pulse from the rectifier circuit is going positive, but it will not charge to as high a voltage as C1 because capacitor C2 must charge through the series resistor. As the pulse drops in amplitude, both C1 and C2 will discharge through the load. This tends to keep the output voltage at close to the peak value of the applied signal. The voltage across the load will steadily decrease until the capacitors start recharging back to their peak values. As you can see, this still does not produce a pure DC output. The heavier the load, the faster the capacitor will discharge. Since the amount of capacitor discharge depends upon the load connected to the circuit, if there is no load connected across the filter circuit, the capacitor will have no discharge path, and they will retain most of the original charge between the applied pulse. Therefore, to properly test this type of filter circuit, you must have a load connected to the output. The size of the capacitor will also affect the voltage fluctuation at the output. The larger the capacitors, the more filtering action will take place. Next, we shall look at the effect of placing a choke in series with the rectified output. The choke will tend to oppose any buildup of current when the rectifier conducts, and it will try to maintain the current flow when the rectifier is not conducting. This is due to the fact as the current increases, the electromagnetic lines of force cutting across the coils in the choke will produce a counter-electromotive force that will resist any change of current. As the current across the coil decreases and the magnetic field collapses back across the coil, it produces another counter-EMF that tends to keep the voltage the same across the load. A practical filtering system will usually consist of both capacitors and choke because they complement each other to provide for optimum filtering action. In both the capacitor input filter and the choke input filter circuits, the capacitor will store the energy as the applied voltage is increasing, and it releases the voltage to the load as the applied voltage falls. In the same respect, the choke will tend to oppose any change in the current flow through it. Here we see a different capacitor input filter. If you notice, a capacitor appears on the rectifier side of the choke. Because of its shape, this capacitor input filter is often referred to as a pi filter network. This capacitor input filter will attain a greater peak voltage during the period when the rectifier is conducting, because the input capacitor will have a very low input impedance as the capacitor is charging to the peak voltage value. Under a no-load condition, the voltage at the filter output will be nearly the peak voltage supplied by the rectifier circuit. The voltage will drop considerably as the load is attached to the output. Therefore, the no-load to full-load voltage regulation of this filter is poor. Here we see a choke input filter. As you can see, the choke appears on the rectifier side of the filter circuit. The choke will allow the DC component of the rectified output to pass freely, but it offers a high impedance to the AC component of the signal. Any AC signal that does not pass through the choke is further reduced in amplitude by the filtering action of the capacitor. This is because the capacitor has a low reactance to the AC current and therefore bypasses it so it does not reach the load. The output voltage from the choke input filter will stay fairly constant as long as the load current is not allowed to drop below a certain minimum current level. When using a full wave or bridge rectifier circuit operating from a 60 Hz power line, you can calculate for the maximum load resistance in ohms that can be used to maintain good voltage regulation. To do this, use the formula 1130 times the value of the choke inductance in henries. Now, to calculate for the minimum current to which this circuit may be operated, divide the output voltage from the filter by the maximum load resistance of the circuit. The current should not drop below this value if good voltage regulation is to be maintained. Oftentimes, a bleeder resistor is placed across the output of a choke input filter circuit. This is used to maintain a constant minimum load across the filter circuit to obtain the best voltage regulation. The bleeder resistor is also used to drain off any voltage which may be stored by the capacitor after the equipment has been shut off. Now that we have discussed the rectifier and filter sections of a power supply, let's examine some typical power supplies to see what they look like. The first power supply we shall discuss is the AC-DC power supply. This power supply does not use a power transformer. Instead, it operates directly from the input AC power. You will find this type of power supply in low-cost equipment. The first AC-DC power supply was designed for use in low-cost table model radios. The radios were supposed to operate from either an AC or DC power line. When operated by a DC power line, the maximum voltage that the power supply could produce was the DC line voltage. However, when the radio was operated from an AC power line, the capacitor input filter circuit would produce a voltage of 1.4 times the line input voltage. Unfortunately, most of the time when you attempt to use one of these radios on the DC power line, it just wouldn't work. Today, DC power lines have all but disappeared. Even though these power supplies are used exclusively for AC input, the old name has stayed with it. Notice the resistor connected between the diode and the power line. The purpose of this resistor is to keep the diode from being destroyed when the supply is first turned on. When the equipment is first turned on, capacitor C1 will be discharged. Without resistor R2 in the line to limit the current, the initial charging current through the diode could be high enough to damage the diode. Even though this power supply was designed for use in radio receivers, you will find similar power supplies in other types of low-cost equipment. Here we see a basic full-wave power supply with a capacitor input filter network consisting of two capacitors and a choke in a pi configuration. You will also notice that this power supply uses a power transformer with a center tapped secondary winding. Since this power supply uses a capacitor input filter network, the output voltage will vary greatly with changes in the load resistance. Therefore, this type of power supply should be used in low current applications if good voltage regulation is to be maintained. Here we see another power supply capable of supplying multiple output voltages. At first glance, this power supply may look complicated, but actually it's made up of two power supply circuits which we've already discussed. This power supply consists of a bridge rectifier with an LC filter and a full wave rectifier with an LC filter. Also, both of these rectifier outputs have bleeder resistors across the output of the filter circuits. The bleeder resistors are also being used as voltage divider network. Therefore, this supply has a total of 4 output voltages. The total output voltage from the full wave circuit will be approximately 1/2 the voltage supplied by the bridge rectifier, because the full wave rectifier uses a center tap transformer and therefore only uses half the secondary coil at a time. Most modern pieces of electronic equipment will use either the full wave or the bridge rectifier type circuits. Of these two, the bridge circuit is most widely used because of the cost saving from not using the center tap transformer. Many times the bridge rectifier is used with no transformer, and the bleeder resistors are used to form a voltage divider network to produce the proper voltage levels. Also, most modern power supplies will use the pi-type filter network. We will now review some of the material just discussed. Rectifier circuits produce ripple voltage. Since this voltage is not constant in magnitude, a filter circuit is necessary. Most power supply filters are basically low-pass filter circuits that block all frequencies greater than 0 Hz. The two basic types of filter circuits are choke input circuits and capacitor input. RC filters are not very efficient because of the voltage drop across the series resistor. The heavier the load current, the larger the voltage drop. Coils and capacitors by themselves will not provide sufficient filtering action. Therefore, they are commonly used together. Bleeder resistors are often placed across the output of a filter circuit to maintain a minimum current level and to discharge the capacitors when the power supply is turned off. Bridge rectifier circuits may be operated with or without a step-down transformer. This concludes review number 2. Now that we have a basic understanding of power supplies, let's examine some voltage regulator circuits and see how they are used in the power supply system. The function of the regulator circuit is to reduce fluctuations in the output voltage due to changes in the load or input voltage. Most power supplies will have some form of regulator circuit. In the ideal power supply, the no-load to full-load voltages will be the same. In practical systems, however, the differences between these two values is an indication of the power supply's ability to regulate the output voltage at a desired level. Therefore, low percentages of voltage regulation are desirable. The smaller the percentage of regulation, the better the power supply. Well-designed power supplies will have regulations of less than 0.01%. The Zener diode with a series resistor makes a simple but efficient voltage regulator. The characteristics of the Zener diode are such that its voltage will remain almost constant over a wide range of currents flowing through it. The series resistor should be chosen to limit the Zener current to a maximum safe level when no load is connected to the output. The Zener current should be about 20% of the current flowing through the load. When a load is connected, the Zener current will drop, but the voltage will remain constant as long as the load current does not exceed the maximum current level. The load is connected in parallel with the Zener. The current in the series resistor will be the sum of the load current and the Zener current. As more current passes through the series resistor, it will have more of a voltage drop across it. If the load draws too much current, the Zener current will not be sufficient to sustain the avalanche current of the Zener, and the regulation will not be maintained. If you noticed, the Zener is operated in the reverse bias mode. This is the normal operating mode of a Zener diode. There are two basic types of voltage regulators, shunt type and series type. The Zener regulator circuit we just discussed is a simple shunt type regulator because the load is placed in parallel with the Zener. The shunt regulator is actually very inefficient, but it does possess the advantage of not being destroyed under short circuit conditions. If the input voltage increases, the current through the Zener will increase, and so will the voltage drop across the series resistor R1. The Zener voltage will remain about the same. If the input voltage decreases, the current through the Zener will also decrease, and the voltage drop across the series resistor will also decrease, thereby regulating the output voltage. One of the major disadvantages with the Zener diode is the effect that temperature has on the reverse breakdown voltage. Zener diodes rated at less than 6 volts will have a negative temperature coefficient. Zener diodes rated above 6 volts have a positive temperature coefficient. As the temperature increases, so does the breakdown voltage. Zener diodes rated at 6 volts will have almost a 0 temperature coefficient. Therefore, the 6 volts Zener is very stable with temperature changes. By connecting a normal silicon diode in series with a Zener rated above 6 volts, a temperature compensating circuit can be designed for use above 6 volts. This is due to the fact the temperature coefficient of a normal forward bias diode is negative, and the temperature coefficient of a Zener rated above 6 volts is positive. Therefore, one diode will compensate for a change in the other as the temperature increases. Since the silicon diode has a voltage drop of 0.7 of a volt when forward biased, it will add to the voltage drop of the Zener. As an example, a 12-volt Zener in series with a forward bias silicon diode will produce a 12.7 volt regulated output. Here we see another simple shunt regulator, but as you may have noticed, this one uses a transistor. The shunt regulator works by shunting current away from the load in order to reduce the output voltage. For example, if the voltage at the output is too low, then the shunt regulator will shunt less current from the load. The voltage drop across the series resistor R1 will determine the output voltage. The more voltage drop across the resistor R1, the less will be available for the load at the output. The Zener voltage plus the base to emitter voltage of Q1 will equal the load voltage. If the load resistance increases, it will cause the voltage at the output to increase, and the current through the load will decrease. Because when the voltage at the output increases, it will cause the forward bias voltage on the transistor to increase. This in turn will cause the transistor to turn on more and conduct more current. This increased current from the transistor then flows through the series resistor. Ohm's law states that the voltage equals resistance times current. So when the current increases through the series resistor, so will the voltage drop across it. Since more voltage is now being dropped across the series resistor, less voltage will be available at the output for the load. In effect, the increased voltage at the output has been corrected due to the compensating characteristics of the shunt circuit. The shunt regulator circuits we have studied are quite satisfactory and economical as long as the current required for the load is not too high. As long as the load does not exceed 5 watts, this type of circuit will do a good job. For higher power applications, above 5 watts, it is better to use a series voltage regulator circuit. The series regulator will use a variable resistance device like a transistor in series with the load. If the input voltage or current changes, the transistor will adjust itself to compensate for the change. The Zener diode in this circuit is used as a reference voltage device to apply a fixed voltage at the base of the transistor. R2 is used to bias the base of the transistor depending on the current flow through the Zener diode. Let's see how this circuit works. If the load voltage increases due to a change in the load, it will result in a voltage decrease across the emitter base junction bias of the transistor. This is due to the fact that as the output voltage increases, so will the voltage drop across resistor R2. Since the voltage drop across the Zener will not change, then the voltage drop across R2 must change. When the voltage drop across R2 increases, it causes a decrease on the forward bias voltage across the emitter base junction of the transistor. When the forward bias voltage of the transistor decreases, it causes the transistor to conduct less current for the load. Therefore, the voltage drop across the transistor will increase, and the voltage drop across the load will decrease, thereby keeping the output voltage constant. In all regulating circuits, the regulating device will act as an automatic variable resistor. The resistance of the device will change so it will provide more or less current to the load, thereby keeping the output voltage constant. Also, input voltage must be a few volts higher than the desired output voltage for proper operation of the regulator circuit. Here we see a block diagram of a series feedback regulator circuit. In this circuit, the sampler is the sensing element of the system. It is usually a voltage divider network and is used to sample part of the output voltage. The sample voltage and the reference voltage are both fed into the error detector circuit. The error detector circuit will compare these two voltages. The error voltage is then amplified by the DC error amplifier. The signal from the error amplifier is used to control the series transistor, which is used in the control section of the circuit. The controller is used to adjust the output back to the desired level. Here we see a simple feedback voltage regulator circuit. Q1 is the controller device in this system and is connected in an emitter-follower configuration. The base of Q1 is controlled by the combination of Q2 and R5. Q2 performs two functions in this circuit. It is used as the error detector and as the DC error amplifier. Zener diode D1 is used as the reference source, and resistors R1, R2, and R3 form the sampler circuit. Let's examine this circuit and see how it works. In this example, we will assume that the output voltage is too high. A sample of the output voltage is taken from the voltage divider circuit via R2. This sample voltage is then fed into the base of Q2. The emitter of Q2 is biased by the Zener diode D1 and resistor R4. The Zener is used to provide a fixed voltage on the emitter of Q2. Q2 then compares the reference voltage and the sample voltage taken from R2. If the output voltage increases, it will cause the emitter base junction of Q2 to turn on more and conduct more current into resistor R5. The base bias for Q1 is obtained from resistor R5. The current through this resistor is a combination of the base current of Q1 and the collector current of Q2. As the collector current from Q2 increases, it increases the current flow through R5. As the current flow through R5 increases, so will the voltage drop across it. As the voltage drop across R5 increases, it decreases the forward bias of Q1. This in turn causes Q1 to conduct less current, and the resistance of Q1 will increase. As the resistance of Q1 increases, so will the voltage drop across it. This leaves less voltage for the load at the output of the power supply. As you can see, the original output voltage increase was corrected. Now let's see what would happen if the output voltage to the load was too low. Since the output voltage is low, the voltage sampled by Q2 will also be low. This causes Q2 to conduct less current. Since Q2 conducts less current, it provides less current through the bias resistor R5 of Q1. This in turn causes the voltage drop across R5 to decrease. When the voltage drop across R5 decreases, it effectively raises the positive bias being applied to the base of Q1. This is due to the fact that the voltage drop across the Q2 D1 combination increased, thereby causing the bias on Q1 to increase. When the bias on Q1 increases, it causes the voltage drop across Q1 to decrease, thereby allowing more voltage to be used by the load of the circuit. Remember, voltage is equal to current times resistance, so when Q1 turns on more, it allows more current to flow through the load. When the current through the load increases, so will the voltage drop across it. As you can see, when the voltage across the load decreased, the circuit automatically sensed it and corrected it. R2 is used to adjust the output voltage of the regulator. Once it is set, the circuit will automatically maintain the output voltage at the desired level. While some electronic circuits still use voltage regulators constructed with discrete components, more and more integrated circuits are being used for this application. There are a wide variety of integrated circuit voltage regulators available on today's market. Some of these devices require no external components other than a power source for proper operation. Here we see just a few of these devices. One of the most widely used IC regulators is a 3-terminal device. It is packaged in a standard power transistor enclosure. The 3 terminals on the IC are the input, regulated output, and the common terminal. The unregulated input voltage is applied between the input lead and the common lead. The load is placed between the regulated output lead and the common lead. This style voltage regulator is available in a wide range of current and voltage ratings. They are also available in both positive and negative outputs. The 3-terminal regulator is normally used to support only portions of an electronic circuit because they can only handle modest amounts of power, typically up to 1 amp. The IC regulator is designed for point-of-use regulation. What this means is that the individual subsystems will each have their own regulator mounted on the printed circuit boards instead of having one single regulator in the power supply. This has actually helped the technician's job somewhat because circuit malfunctions which might affect the power supply output are in most cases confined to the printed circuit board on which they occur. This style regulator usually contains protective circuitry that will shut the device down if its internal temperature becomes too high. Therefore, if the load draws too much current, or if the input voltage goes too high and causes a large power dissipation within the device, it will cause it to shut down. In most cases, the regulator will resume normal operation when the excessive heat has been dissipated. More and more circuits are using the integrated circuit voltage regulators instead of discrete component regulators because they are smaller and require less space and less electrical connections. Also, these devices usually contain built-in overload protection circuitry. They are also less expensive than regulators using discrete components. All the regulator circuits described so far suffer from a common disadvantage. They are somewhat inefficient because they regulate the load and the line variations by dissipating the power internally in the form of heat. Since this power is lost when it is dissipated by heat, it will not be delivered to the load. As the power consumed by the load increases, so will the power being lost by heat. Large series and shunt regulators must be cooled with heat sinks to dissipate this extra power being lost in the device. Because of this disadvantage, power supply designers have developed an alternate approach to the regulator design. The switching regulator is one of these alternatives. Here we see a switching regulator circuit. As you noticed, it contains a series pass transistor, a voltage-controlled oscillator, and a comparator circuit, as well as a filter circuit consisting of D1, L1, and C1. The series pass transistor is a switching transistor that does not conduct continuously. Instead, it is either operated in the saturation mode or in the cutoff mode. The series transistor is controlled by the voltage-controlled oscillator. The VCO will output a series of pulses into the base of the transistor, thereby controlling the on-off state of the transistor. The on-off pulses from the series pass transistor are filtered to produce the output voltage. The filter circuit is basically a choke input filter with a diode. This circuit is accomplished by varying the pulse repetition rate of the series pass transistor. The voltage from the transistor is stored in the electromagnetic field of the choke L1, and it is further filtered by capacitor C1. The output voltage from this circuit will be the average. The output voltage from the filter is fed into the load and into the comparator circuit. The comparator circuit is designed to sense the voltage at the output to the load. Resistors R1 and R2 are chosen to set the regulator for the desired output voltage. The primary purpose of diode D1 is to protect the transistor from the inductive kick of the filter choke that occurs when the transistor switches from saturation to cutoff. The VCO will output a series of pulses whenever the output voltage drops below the threshold level to restore the DC output level. The frequency of the VCO will depend upon the requirements of the load. Typical operating frequencies from a switching regulator circuit will range from 10 kHz to 500 kHz, which allows the filter components to be quite small. Since the transistor is either on or off during its normal operation, it will dissipate a relatively small amount of power as compared to the previous regulators. Since this style regulator uses smaller components and does not normally need a heat sink, its size may be as small as 1/3 to 1/2 of that required for the regular series regulator circuit. Many devices require a constant current instead of a constant voltage for proper operation. Therefore, these devices require a different form of regulator, the current regulator. Here we see a simple current regulator circuit. Notice that a PNP transistor is used in this circuit. Also notice that the Zener diode and the Zener resistor have exchanged places. The transistor's bias voltage between the base and the emitter will equal the difference between the Zener diode voltage and the voltage drop across the Zener resistor. If the load current increases, the voltage drop across the Zener resistor will also increase. This then changes the bias voltage being applied to the base of the series pass transistor. It will cause the bias voltage to decrease. This in turn will cause the current flowing through the transistor to decrease to compensate for the original increase in the load current. Current-sensitive devices like magnetic cores, meters, relays, transistors, and diodes are among the many devices commonly operated with constant current power supply sources. We will now review the regulator circuits just discussed. Zener diodes make very inexpensive voltage regulators. They are generally found in low-power applications. Zener diodes rated below 6 volts have a negative temperature coefficient. Zener diodes rated above 6 volts have a positive temperature coefficient. Zener diodes rated at 6 volts will have almost a 0 temperature coefficient. The shunt voltage regulator controls the output voltage by providing a second path for the load current to flow. By reducing or increasing the current to the load, the voltage can be maintained. Shunt regulators are used primarily in low-power applications and are very inefficient. Series voltage regulator controlling the amount of current allowed to pass through the load. This is accomplished by means of a series pass transistor. The series feedback regulator circuits consist of 5 basic blocks. These are the sampler, reference device, error detector, error amplifier, and the control device. IC regulator circuits are common in today's modern equipment. The output and the common. The IC regulator has found discrete devices have fewer connections, are less expensive. Since the shunt and series type power not used by the load in the form of heat, they often require heat sinks. The switching regulator controls the output voltage on and off at a high frequency. This frequency may range from 10,000 to 500,000 cycles per second. The series pass transistor is controlled by a voltage-controlled oscillator. The frequency of the VCO will change with the requirements of the load. The switching regulator is generally much more efficient than are the shunt or series type regulators. This concludes review number 3. The last circuit we will discuss is used for overvoltage protection. Fuses and circuit breakers are power supplies. Oftentimes, these devices do not react quickly enough to protect today's sensitive devices. Here we see an SCR crowbar circuit, which is used for overvoltage protection. A silicon control rectifier and a current source that monitors the voltage on the power supply. During normal operation, the SCR and transistor Q1 do not conduct current. Contacts from relay K1 are wired in series with the power transformer primary, and transistor Q2 is used to energize relay K1. In this circuit, the Zener diode has a breakdown voltage equal to the voltage at which you want the overvoltage protection to occur. This should be somewhat higher than the normal power supply voltage. Under normal operating conditions, the voltage of the power supply is not high enough to cause the Zener to conduct, so there will be no current flow through it Since R1 has no current flowing through it, there will be no voltage drop across it. Therefore, Q1 will not be forward biased and it also will not conduct current. Basically, Q1 will act like an open circuit. As long as Q1 is not conducting, the SCR will remain turned off. While the power supply is operating, transistor Q2 is forward biased and turns on. This allows the current to flow through the relay coil and energize it. This causes the contacts on the relay K1 to close and maintain power to the power supply. In the event of an overvoltage condition, the Zener diode will turn on and conduct current through resistor R1. As the current flows through R1, it develops a voltage drop across it. When there is a voltage drop developed across R1, transistor Q1 will forward bias and turn on. When Q1 turns on, it will produce a positive gate signal for the SCR. This in turn will cause the SCR to start conducting a heavy current from the negative side of the power supply to the positive side of the power supply. In effect, the SCR will short out the power supply. When the SCR shorts out the power supply, it will drop the voltage of the power supply down to almost zero. When the output voltage from the power supply drops, it will cause Q2 to quit conducting. When Q2 stops, the relay to open and shut off the power to the primary side of the transformer. This in turn shuts the power supply down and be turned back on. Diode D1, which is connected across the relay, serves no useful purpose while the relay is energized. However, when Q2 stops conducting, the sudden drop in current through the relay coil will produce a counter-electromotive force which will tend to keep the relay energized. The polarity of the counter-EMF will be such that it will forward bias diode D1 and cause the voltage being produced by the relay coil to dissipate rapidly so the relay will open. Now that we have discussed the basic circuits found in most power supplies, we will discuss how to troubleshoot and isolate power supply problems. Defective power supplies usually affect the performance of the entire system. This is due to the fact that many systems are operated from one common power supply. Sometimes the defects are caused by failures within the power supply, and other times it will appear that the defect is in the power supply when in reality it will be caused by a failure in other parts of the system. Therefore, before assuming that the fault lies within the power supply, check the subsystems being fed by the power supply to establish that the subsystem loads have not changed. To accomplish this, disconnect the load from the power supply and monitor it with an oscilloscope. If the power supply checks good, then apply a load of proper resistance and current rating to the output of the supply and monitor it with the oscilloscope again. In the discussion that follows, it is assumed that the load does not contain the defect, and the fault definitely lies within the power supply. Regulated power supply problems are usually grouped into two categories. First, loss of regulation, and second, excessive ripple. Loss of regulation will cause improper output voltages, and excessive ripple will result in a large AC signal component on the output voltage. Testing a power supply usually requires a simulated load, a digital voltmeter, and an oscilloscope. Waveform and voltage measurement must be made as the load is varied from a high resistance to a low resistance. Anytime it indicates a filter or regulator problem. A problem of no output voltage usually indicates rectifier or transformer problems. If there is excessive ripple, This is an indication of a filter failure. Typical transformer problems include shorted turns in either the primary or the secondary windings, or the windings may be shorted to the core. Usually a shorted transformer will result in a blown fuse. If the fuse does not blow, it will cause the transformer to overheat, and the output voltage will drop significantly. Transformer wind open instead of shorting, in which case it will not blow the fuse, but the output voltage will drop to zero. Open or shorted windings in a transformer may be checked by making resistance measurements. Typically, rectifier diodes will only fail in one of two ways. They are either open or shorted. A quick check with an oscilloscope can provide you with much information about the diode. If you are testing a full wave rectifier and one of the diodes has opened, then output will resemble a half-wave rectifier. Diode, on the other hand, will normally cause a fuse to open. This is because on alternate half cycles, the secondary winding will be short-circuited, which will cause excessive transformer current. Checks. It will be necessary to measure both the forward and reverse resistance of the diode. Most modern DMMs show low resistance in one direction, and an open circuit reading in the other direction. The exact value of these readings will depend on the characteristics of the diode under test. Filter problems usually result in excessive ripple or no output. If one of the filter capacitors opens, it will cause the output voltage to drop and produce excessive ripple into the regulator circuit. Capacitors usually develop current leakage before they short. This will cause the capacitor to get warm. If the filter capacitor shorts, it will usually inductor may cause the fuse to blow, or it will produce excessive ripple at the output of the power supply. An open resistor or inductor in series, part of the filter, will cause the output voltage to drop to zero. Resistance checks will vary or open inductor or an open resistor. The regulator section is the most complicated part of the power supply. The best way to test the regulator is to vary the load resistance while monitoring the output voltage. Large variations in the output voltage indicate a malfunction in the regulator circuit. If the regulator has no output voltage, then suspect an open series pass transistor. Since most regulator circuits use a Zener diode to establish the reference voltage of the circuit, a problem of a shorted Zener would cause the output voltage to be very low, since this would bring the emitter of the transistor to ground potential. A shorted Zener may also cause the series pass transistor to overheat. If the regulator does not respond to changes in the load, the output voltage may be higher than normal. This is usually caused by a defect in the transistor, which controls the series pass transistor. Most problems in the regulator section are easily isolated by making voltage measurements with the oscilloscope or the DMM. In this video, we have seen that rectifiers are used to convert the AC sine wave from the transformer into a pulsating DC. Filtering is required to smooth out the pulsating DC into a usable DC voltage. Regulators are used to maintain the voltage at a preset level under different load conditions. This video does not cover every power supply you will encounter in your career in electronics, but it should give you a good idea of how the power supply functions. You should review this video often because most of the equipment you will encounter as a technician will have a power supply for its source of energy.